All right. Welcome everyone to today's live stream. Today we have Mohammed Sedik, a PhD student at UC Santa Cruz. He'll be talking about condensed matter physics, specifically the Ising model, and a computational approach for looking at phase transitions in the Ising model. All right, go ahead, Sedik.
Thank you, Dugan. So I will be talking about phase transitions in general, and I'll talk specifically about the Ising model. Like the goal of the presentation today is to showcase an idea that I did in the Wolfram Winter School 2025. It's a simple idea, but it's like it's a new way to look at phase transitions, or to look at the Lee-Yang theorem specifically from a computational point of view. So here is the outline of what I'm gonna do today. I will first talk about like generically about what is phase transition, and then I will talk about the classifications of different phase transitions. I will talk about the Yang-Lee formalism. It's basically a formalism of phase transitions, of studying phase transition, but it's not so common. So I wanted to introduce it. And then within this formalism, there is a famous Lee-Yang theorem. We're also going to talk about it and give examples on how this formalism actually makes sense. Then I will show a computational approach to this Lee-Yang theorem to understand it from a computational point of view rather than from a mathematical point of view. Okay, so I first want to start with what is phase transition. So generally, phase transition is any abrupt or discontinuous change in a system that happens when the system has many components, not just one or two components. Like it has to be like a large system, and this is usually identified as you change a parameter, a control parameter of the system. So something like when you change the temperature or we change the pressure, you change magnetic field, those are parameters that you have. And then based on this parameter, your system goes from one phase into another phase. So the famous example for this is liquid evaporation at high temperature. So if you have a liquid and you change the temperature, keeping the pressure fixed, the liquid turns into gas. So this is the liquid gas phase transition. The gas condensed the other way around. Like if you lower the temperature for a gas, it will turn into a liquid. And then they also have another example that is the collective magnetization in a magnetic material. So if you have a magnetic material at very high temperatures, they lose their magnetic properties. But as you lower the temperature, they do have finite magnetization. Like yeah, most of the magnetic materials are like this, and this is also called the phase transition from non-magnetic to magnetic as you lower the temperature. So I will just show case what happens in the liquid gas phase transition. So in the phase transition, we plot something called the phase diagram. Phase diagram is basically all the parameters associated with the system are plotted. So in the case of when people consider a gas or a liquid, people consider van der Waals gas, which is basically a collection of molecules that are not interacting with one another. It's more like hard spheres bouncing off one another. That's like the simplest way to see a transition between liquid and gas. So on the graph here, can you see my cursor?
Yeah.
Yeah. So on the graph here, you see there is a temperature axis and the pressure axis. So and you could see this region that is called gas and this region that's called liquid. That is basically, so if you have a temperature given by this value and a pressure given by that value, so you know the point Tp lies in this region, it means your system is going to be in a gaseous state. If it lies in this region, it means your system is going to be in a liquid state. So the transition basically happens like, you know, if you fix the temperature and you keep changing the pressure up and you start from very, very low pressure. So at a given temperature, at very, very low pressure, the gas molecules are like, they are not compressed together. They want to bounce off one another. So they are more like roaming around in the volume that you're given, which means, you know, you're gonna have a gaseous state. But as you increase the pressure, as you keep increasing the pressure, after this curve, after some value, you're gonna keep condensing them until they turn into a liquid. So this is a very basic view of phase transition, of the liquid gas phase transition. It's given by van der Waals gas. So what's really interesting about this phase transition is that there is a curve of coexistence. So you could ask, what if I am exactly at this point? So it's at this point, your system will be like partially in the gaseous state and partially in the liquid state. And there is some exchange between both of them going on, like gas turning into liquid and liquid turning into gas, but in a almost an equal manner. So they both still exist as time goes on. Does this make sense? Okay.
Yeah, yeah.
So yeah, and there is at the end of this like coexistence curve, we have a critical point, and this critical point is basically a given T and TC and PC, where like if you are at a temperature above this critical temperature, you cannot turn between liquid and gas. And there is a reason why we don't put any label in this region. It's just like the system itself cannot be distinguished if it's gas or liquid. It's usually called something like super fluid or something like this. So not to be confused with the super liquid, not to be confused with the super fluid from the other phase transitions. So it's just like the system itself is not in a state that could be distinguished as gas or liquid. This seems a little hand wavy, but the rigorous way of doing it is by defining something called the order parameter, and I'm going to talk about it more in the magnetic case. The order parameter is like, it's a property of the system that tells you which phase you are in. So here, the order parameter is basically the difference between the density of the gas in your system and the density of the liquid in your system. This difference is called the order parameter. So like, when it's in the gas, this order parameter is 0. When it's in the liquid, this order parameter is finite. That's it. So here the order parameter is just not defined. So that's why you can't really tell if it's in the gas or in the liquid. What's really crucial about this phase transition is when you study, like it's a system. It has temperature, it has pressure, it has given volume. We could study the thermodynamic properties of this system or the macroscopic properties of that system. And when we study it, we see that upon transitioning from gas to liquid, we're gonna see that there is some latent heat. So basically, for a given pressure, as you're walking like this, as you're walking across, as you're changing the temperature, you see that when you transition from liquid to gas, the system needs to absorb some heat. And this heat is given by integral over T ds, where S here is the entropy. And like if one works out all the math, you find that the free energy of the system undergoes a discontinuity. And this is basically the discontinuity that we talked about in the abruptly change of the system. So here we describe this discontinuity by the discontinuity in the Helmholtz free energy. Does this make sense?
So you're integrating over entropy. That's what the DS you said was.
Yes, that's the entropy. So like Q is not an exact differential. So technically what happens is like also every point here is supposed to be in equilibrium. Like when we say here TMP, we mean like the system reached equilibrium here. So the way you move from one point to another point is you move very, very minor change and you wait until the system stays in equilibrium, and then you measure, and then so on. So I think what people do in experiments, and these experiments have been like done way before advanced physics or modern physics. So what they do is like they change the system a little bit, they see the change in entropy, and then you just multiply it by the temperature, and you keep adding those things up because there's not a functional form of T. Yeah, and then you just see that like there is this Q is because Q is finite, then there has to be a discontinuous change here in the first derivative of F with respect to T on the gas side and the liquid side. Does this make sense?
Yeah.
Yeah. So now we associated the discontinuity here with a discontinuity in the first derivative of the Helmholtz free energy and the absorption or release of latent heat. if you go from gas to liquid or liquid to gas. So yeah, another famous example is in magnetism. So I'm gonna spend a little more time talking about magnetism. So magnetic materials are those materials that have intrinsic magnetic moments inside of them. So basically, their atoms have some their molecules, let's not say atoms, their molecules have some magnetic moments intrinsic to them. So if those magnetic moments are aligned together, all of them in the same direction, you're gonna find a finite global magnetization in your material. Which means like your material is gonna respond to magnetic fields, or it's gonna attract another magnetic material, or so on. So if they are all aligned, we call this ferromagnetic state, where there is finite magnetization. There is another property, another case where like they are anti-aligned, up and down, up and down, up and down. And in this case, if they anti-align, there is no net magnetization. Like every magnetic moment from here and magnetic moment from here will cancel one another. So you're not gonna get any total magnetic magnetization macroscopically, and this is called anti-ferromagnetic. There is something called the ferrimagnetic that has been picking up interest recently in experiment, where it's exactly the antiferromagnetic, but the moments are not of equal strength. So, for example, you get a spin of value 1/2, another spin of value 3/2. So, like effective spin of an atom. So you see that yes, they could be anti-aligned, but they don't perfectly cancel, and there is still some finite magnetization that could be done. So this is also an interesting case, but we're not going to talk about it. And the other case is like they are all the magnetic fields, the magnetic moments are randomly aligned, which means it's not going to have any magnetization macroscopically. The interesting part is how these paramagnets respond to a magnetic field. So although they are naturally anti-aligned, if you apply a magnetic field in this material, each one of those spins want to align with the magnetic field. Whether you like, if you apply an up magnetic field, those spins will actually flip to go into the up direction. And you gain from the paramagnetic, you gain a ferromagnetic state by applying magnetic field. Does this make sense?
Yeah, so for the ferromagnetic, the like in this diagram, you have like larger moments in the down direction versus the up direction. Would that be made by like having larger domains aligned downward and then having smaller domains aligned upward?
For the ferrimagnet?
Uh-huh.
No, I think it could be done this way. I'm not sure if I'm not sure if there is an argument that prevents it from happening this way. But people don't think of this as domains. They think of this as the actual magnetic moments aligned opposite to one another, and this would come from a material where you have different magnetic moments, like two different kind of molecules. Each of them
Okay.
have its own magnetic moment, like a more complex compound would give a ferrimagnet. That has like different kinds of magnetic moments inside of it.
Got it. So it's a different in types of the atoms that are having moments,
Yes, exactly.
magnetic moments.
Yeah. So yeah, that's it. Feel free to stop me at any time if you have any questions. I'm fine with that. It's
What's the Curie temperature?
What's the Curie temperature?
Uh-huh.
Yeah. So it's basically the temperature at which the paramagnet becomes a ferromagnet naturally without applying magnetic field.
So you increase the temperature past this, and then some of the moments due to jostling, due to the temperature, get randomly flipped.
Yes.
And then it becomes one of these other types, ferromagnetic.
Yes. Does this make sense?
Yeah, does that pick up so you're saying like after a certain temperature, it'll naturally align itself with spin up or spin down in some direction, or there'll be an alignment?
Yes, and this is a really good point. Like they either have to pick, the system has to pick up or down, mostly.
Well, yeah, there'll be a consensus amongst the atoms,
yes,
and they'll sort of go to align with themselves to a majority.
Yes, and we're gonna, this part is basically what identifies a phase transition here. It's like, of course, we could talk about the two phases, like the
Hmm.
paramagnet and the ferromagnet, but if you can, if you think about it, like, you know, going from the paramagnet to the ferromagnet, as you lower the temperature, like all the spins will be aligned with one another, effectively. And what you want to think about is like, okay, of course, it's not going to happen suddenly, like what happened with the gas and liquid. It's not going to be that abrupt. You apply heat and then the system just keeps moving into a gaseous state. No, in fact, it just like those two spins are going to flip, but this one is going to wait for like even lower temperature to go. So there's more of a continuity happening there. And we're going to also discuss this and its relation to the domains that you talked about, because you know, like, you don't expect the whole system to behave to react to the same change at all location globally. It just doesn't make much sense. But yeah, we're gonna discuss this in the next slide. So we're gonna consider a paramagnet and like a system of magnetic moments. We're gonna apply magnetic field at high temperature and at low temperature, and we're gonna see what happens. So this graph plots the finite magnetization, like something that can distinguish between these two is this has finite magnetization, this does not have finite magnetization. So we see that if we are at a very low temperature, like T less than Tc, and as I change the magnetic field I apply from positive to negative, I see that if I apply a positive magnetic field, all these spins are aligned with the magnetic field. I have finite magnetization. As I lower the magnetic field on the green curve, as I'm moving, it's a fixed temperature. It's an idotherm. So as I lower the magnetic field um, all the way up to zero, now I don't have magnetic field, but I still have finite magnetization. So the system is in ferromagnetic state and it stays in the ferromagnetic state. This makes sense? And I could do it from the other way around. Of applying negative magnetic field and going the other way, I will still have reach at a negative magnetization. So what exactly happens here? It seems to be like experimentally, there will be domains that keep flipping, like it's not gonna happen abruptly. But as we talked about, we wait for equilibrium. We assume that every point is just like, I will apply a new magnetic field and wait until the system equilibrates. You're gonna see that there is some discontinuity. If you are at like a very positive magnetic field and you jump to zero, your system doesn't change. Once you flip your magnetic field and you wait until the system in equilibrium, all the spins are gonna flip. So in the equilibrium point of view, the system actually had like made a jump, a discontinuous jump from positive magnetization to a negative magnetization. Does this make sense?
And this is this in a solid or a liquid?
We're talking about solids here
Yeah.
because
Okay.
liquids are a little, yeah, liquids are going to be a little tricky because they're because like, you know, there's really no way of defining a given moment at a point because they all keep exchanging, like moving around as a liquid. So yeah, no, we're talking about solids here.
Okay.
Yeah. So so yeah, so this is what happens at very low temperatures. At a bit higher temperature, you can still see this happening, but at of course at some like at very high temperatures, um, what you see is um, this you apply a magnetic field, and then as you lower the magnetic field for this very high temperature, it just the magnetic field is forcing the spins to be aligned together, all of them, in the direction of the magnetic field. As you lower it down and at very high temperature, the thermal fluctuation is like thermal fluctuation is basically the tendency for the spins to make random flips.
Hmm.
You know, it's like it starts taking over because it's not like they are not as forced with the magnetic field. So some of the spins will just like, you know, will flip, and when you lose all the magnetic field, it's like now it's perfectly random. So there is no force that tells them, hey, go in align in that direction. So they will just be randomly aligned, and this is called a paramagnetic state where you don't get this. So does this make sense? And the same with the negative part.
Yeah. So
So
this is if it's coming from the extreme where all the three like meet, you're
yeah,
decreasing the external magnetic field strength and seeing how much the
The
rate of
jump is.
flipping, how much
Yeah.
they jump. Now,
Yeah.
is there a discrete jump from the left side to the right side?
From the left side to the right side, yes.
Okay.
Like,
Yeah.
yeah. So because we agreed that every point is like we measure M after we reach equilibrium. It's like obviously in an experiment, if you change H from like 0.0001 to negative 0.0001, you're
Mm.
not gonna see this sudden change. But what you're gonna see is you apply 0.0001 and wait. And then you're gonna measure the magnetization after some long time where the system is in equilibrium. Then you do the flip and you wait a little bit until the system is in equilibrium. And then you see this discontinuous jump because you waited for the equilibrium.
Okay. Okay.
Does it make
So
sense?
this is
Yeah.
each data point here represents after some time letting the
Yes.
system like maintain an equilibrium state, and then you plot that.
Yeah. It's like back to the liquid gas, like
Mm-hmm, mm-hmm.
in what you see when you're boiling water to make some tea is like, you actually apply heat, so you're increasing the temperature of the system at the atmospheric pressure. So you expect at this point, like if this is atmospheric pressure, so you expect at that point that's 100 degrees Celsius. So you expect once the system reaches 100 degrees Celsius, uh, this phase diagram says all the liquid will become gas. That's what the phase diagram says. But that's not what you see in practice. What you see in practice is like, you start seeing the water boiling and
Mm-hmm.
like the gas, the water vapor starts showing. But what we mean by equilibrium is we're gonna put the system on this temperature and in a closed pot or something, and then we're gonna keep it in that temperature for a while. So this while is when it reaches the equilibrium. So eventually, all the water is gonna turn into gas, and if you keep the temperature, it will just stay like this.
Right. Right.
Does this make sense?
Mm-hmm.
Yeah, yeah. That's basically what happens with the magnetic field. It's not a sudden change. Not all spins just decide to flip the moment you flip the magnetic field. But if you wait, all of them are gonna flip, 100%.
Got it.
Yeah.
And if you don't wait, what do you get? The hysteresis curve? It's gonna just
Uh,
continue, or it's not this case.
Yes, no, that is that case. The hysteresis is a dynamical process. It's a non-equilibrium process. So it's like that's how you like you increase the magnetization in your system, or yeah, it's how you get the hysteresis is like you continue quickly enough such that like you change the magnetic field, but the magnetization will keep decreasing until it reaches here. But like it's not gonna be discontinuous like this because now you're plotting at magnetization as you change H like abruptly. Like every moment you change H, you check the magnetization. So you get a curve that's like this curve will continue like this, and if you go in the other direction, that curve will continue like that. And the area inside is called the hysteresis area.
Yeah.
It's like how
So
much magnetization you acquire.
basically, this discontinuous jump is a feature of the equilibrium.
Yes.
Yeah.
Yes. And like that's what we can actually describe because all thermodynamic properties, like here, we keep talking about, wait, yeah, we keep talking about the free energy, about the entropy. All these are equilibrium quantities. Like thermodynamic assumes a system in equilibrium with a given T and P and blah, blah, blah. And you see how you change it such that it stays in equilibrium. That's what thermodynamic is concerned with. So yeah, hysteresis is more of like a E&M class rather than a condensed matter class. Okay, so another thing to do is I could just fix a magnetic field and just change the temperature again in a adiabatic way, such that I wait for equilibrium every time I change. And this time the distinction becomes much more obvious in that way. Like I fix H that is positive value like this. I see that as I increase the temperature, my system always has some finite magnetization. It's like it's always there. So I don't see anything happening when there is a magnetic field. The interesting feature is when I don't have magnetic field. When I don't have magnetic field, like I'm moving along that line and I change the temperature, I see that, okay, if I'm very, very high temperature, the system does not have a finite magnetization. And as you lower the temperature, it will pick up finite magnetization. and then it will just keep increasing, but it is finite. So there should be some distinction between when there is no finite magnetization and there is finite magnetization. There should be some distinction point, right? And this distinction point is what we call the critical temperature, the TC. And that's the Curie point. Does this make sense?
Mhm.
I will show a graph of how I will fix H to be 0 and I will change the temperature. And let's see what this
So
goes.
TC, that's the critical point on the phase diagram you're showing earlier, or is it the Curie temperature?
It's like TC is it's like usually when people refer to a critical temperature, it's just a temperature where there's beyond it there is a phase, and after it there is another phase. Like before and after it there is different phases. That's what they mean by critical temperature. But the Curie point is related to magnetism. Like her work was done on magnetism. Oh, I see now because it's TC, so it could be T Curie, but no, T
Okay, it's
usually is
critical.
for
It's the
critical.
critical part. Got it.
Yeah, TC is always the critical. Yeah. So this is the one that I was talking about. Like if we fix H, just move along that line. We see that at very, very high temperature, I don't have average magnetization on my system. As I lower the temperature beyond a given temperature, the system picks a finite magnetization. Does this graph make sense?
Yeah. So, if there's no magnetization, if it's high temperature and then like it has zero magnetization to it, so that basically all the magnetic moments are randomly aligned
Yes.
and cancel each other out,
Yes.
and then you cool it, will it pick some magnetization? I mean, will it
Yes.
anneal essentially? Is that what this is showing?
It will pick some magnetization, yes. Like it will it's like as you said, they are randomly aligned at high temperature. You start cooling things down adiabatically, and then they want to align with one another because it's
Right.
at low temperatures. So at low temperatures, you're gonna find all of them pointing in a specific direction, and that direction gives the magnetization. It's gonna be a net magnetization when adding all those moments up because they are not canceling. So yeah. Now what you asked about is like it's like, does it pick up or does it pick down? Because like there is no magnetic field that tells them you should go in this direction. There is no magnetic field. So they could like decide to go up, all of them collectively, or they could decide to go down. So what happens is the system actually spontaneously breaks the symmetry between the up and down. It just picks a direction. So like as you lower down, the system could go that way or it could go that way. It could choose this positive magnetization or it could choose that negative magnetization. The value, the finite value is the same, but the sign of the magnetization is randomly assigned. Does this make sense?
Yeah.
Yeah, and this is what we call a phase transition here. And the phase transition is coming from no magnetization to finite magnetization. So when we study this, we find that M is partial F by partial H. That's the magnetization of the system. And F, again, is the free energy of the system. But this time, this first derivative is continuous. In the liquid gas, the first derivative was discontinuous. So this derivative is continuous. And the second derivative is the one that is discontinuous in this phase transition. So we see, although those are two different kinds of phase transition, but we see that they are like the discontinuity is different in both of them. So it's not the same quantity that gets discontinuous. And as we talked before, there is some order parameter, something that tells me which phase I'm in. And here it's pretty obvious that it's the magnetization. In the other one, like it wasn't so obvious. I had to tell you that it's the density, but here it's natural that it's the magnetization that tells you where the thing is, where your system is. And the last thing that we note about this is it does have spontaneous symmetry breaking. There is some symmetry in my system in a phase, and then when the phase transition happens, this symmetry is broken. Like before, I had a symmetry between the up and the down directions. Like the system didn't have any preference between up and down. It's already all randomly aligned. But beyond this TC, like below this TC, you find that the system actually has a preference. The system is now pointing in the up direction. So if you lower even more, you lower temperature even more, the system now prefers that direction. It's not symmetric anymore. So this is called spontaneous symmetry breaking. So why are we going over those two different characterization? So people have done classifications of different phase transitions because people want to study phase transition holistically. And the classification goes as follows. There is a first order phase transition where you see a latent heat absorbed or released. And in this case, latent heat is given by this, which means there is going to be some discontinuity in the first derivative of the free energy. Hence the name first order. So this is what you saw in the liquid gas case. And there is a second order phase transition where you don't have any release or absorption of heat, which means this quantity is zero. So it's the first derivative has to be continuous. And the second derivative is the one that is discontinuous. So, and this second order definitely includes spontaneous symmetry breaking. First order does not necessarily include spontaneous symmetry breaking. And the spontaneity here is coming from the fact that there is no release or absorption. So there has to be something that changes in the system from a mathematical point of view. But here you actually give the system heat. So you tell it, hey, go from this phase to that phase, or you take heat out of it, and so on. So does this classification make sense?
Yeah.
Yeah, it makes sense.
Yeah. There's also like you could have cases where the free energy first order is continuous and the second order is also continuous, but the third order is not continuous. So you could call it a third order phase transition, but people when see this, they will just say second order phase transition. It seems like in the literature or in the community of phase transition, they just decided that things are either first order or second order. So any higher order like discontinuities will still be called second order. It's a little misleading, but just it's a convention, and they don't happen in nature a lot. So that's why it's not a big deal. They're just mentioning it. So yeah. If you noticed, everything we talk about here is in terms of heat, temperature, free energy, and these are all thermodynamic properties. So thermodynamic properties just look at the system as a whole. Like this system globally looks like this. Even when we try to talk about ferromagnetism, although we explain the different states by microscopic picture of the spins or of the magnetic moments, but when we did our actual mathematical study, we talked about the global magnetization, magnetic field, temperature. It's all big picture words. So the question becomes, can we study phase transition from statistical mechanics rather than from thermodynamics? The difference between statistical mechanics and thermodynamics is that thermodynamics is worried about the macroscopic picture of the system, but the statistical mechanics is worried about the microscopic picture of the system. So, for example, if I have a liquid, if I have a system of hard spheres or gas molecules, the thermodynamic wouldn't care where those molecules are or what are their velocities. It would just care what is the temperature of the system, what's the pressure of the system, what's the free energy of the system, and that's it. But like if the statistical mechanics would care about all the possible configurations of this gas molecules, and configurations mean their positions and their velocities. So this is the difference between stat mech and thermodynamics. And people have developed the connection between these two because these two pictures should give you the same final results. They describe the same physical system. And the connection is given by something called the partition function. So the partition function is basically you sum over all the possible microstates or all the possible configurations in the system, and you sum this something called the Boltzmann factor, where beta is 1 over T, or 1 over the inverse temperature, and the energy is the energy of this microstate. So it goes like this. You have a system of hard spheres. You start with one microstate, and you see, okay, each gas molecule has it has a specific position and it has a specific velocity. So the energy of the whole system is just the energy of each molecule, the kinetic energy of each molecule, and the potential energy of each molecule. You add all these up, you get an energy of the microstate. And then you do this for another microstate and another microstate and so on. You do this for all the possible microstates. And when you add all this summation, it gives you the partition function. Does this make sense?
Yeah. So, like in the case of gases, this would be an integral, I guess, over
Yes.
all possible momenta and integrating
And positions.
positions.
Yes.
Okay.
And actually, in the case of liquid gas phase transition, like the integral, like you integrate over all the possible positions and all the possible momenta of the system, but the positions are irrelevant in this energy because we're assuming they're just bouncing off one another. So the position is just like a very hard like what's it called? You just assume that uh, like no two molecules can be on top of one another, and that's it. It should be as simple as that. But the momentum one is also a little simple because they are all of like it just all of them have the same half mv square, so you're just summing over v. It's like a little bit of a more complicated Gaussian, or it is a Gaussian, so it's easy to do. So yeah, and for finite systems that we're gonna consider like the Ising model, the sum is just summing over all the possible microstates. It's finite summation.
Right. So in the icing model, like the position of everything's in a solid, so those are fixed and
Yes.
they're not moving. I guess there might be a temperature component, but that's what beta was for.
Yes, the temperature components are here. So the microstates in the Ising model is basically you have spins. All of them are fixed because it's a model for solids. So everything is fixed. Each spin in a fixed position could be up or down. Now the energy changes by because as we can see, the model is like as you lower the temperature, the spins align together. So they should be talking to one another. So there is, and they introduce this talking by interaction. It's like the spins will have positive energy if they are aligned. They will have like some energy if they're aligned, and they will have a higher energy if they are not aligned. So they are anti-aligned. So the system wants to go to the lower energy, so they want to align with one another. That's the ferromagnetic picture of the Ising model. So the energy here comes from the interaction between those spins, not from like a position of the spin or its value. Does this make sense?
Mhm.
Okay. So what is the connection? The connection between like of course in thermodynamics everything could be given from thermodynamic potentials, which is the free energy. So like a first derivative with respect to temperature will give you the energy, or give you the entropy. A first derivative with respect to magnetic field will give you the magnetization. So a first derivative I think with respect to the volume will give you the pressure. So once you have F, you have everything in the thermodynamic picture. And once you have Z, you have F. So this is the connection between statmech and thermodynamics. Does this make sense? Okay. So yeah. So as we can see from here, all different kinds of phase transition, they have some problems with F, some discontinuity with F, non-analytic behavior in F. So if one wants to study phase transition from the statistical mechanics point of view, we have to see what happens for Z, because that's the one that describes statistical mechanics. So if F is discontinuous, this should be somehow reflected in Z. And this was called the Yang-Lee formalism. Yang and Lee in 1952, they said, okay, rather than studying phase transition from free energy and so on, we're just gonna study it from the point of view of statmech. So they proposed they studied the Ising model with n sites, and in fact, like they studied it in any dimension. It wasn't just the 2 dimension. It could be in any dimension, and it could be in any geometry. Like every site could have 6 neighbors or 4 neighbors or any number of neighbors. So this is the Ising model Hamiltonian. So you see that the magnetic field, like we have magnetic field introduced right now. So the energy, if sigma I and sigma j take values plus or minus 1, so if this is plus 1 and this plus 1, which means up, up, this is going to give you 1. And the same if they are both minus 1 and minus 1. They're going to give you 1, which means because of this negative sign, it lowers the energy of the system. And what about the magnetization? If H is positive, like up magnetic field, then sigma wants to be positive, so this quantity reduces the energy even further.
Mhm.
Does this make sense?
Yeah, so you have like a neighbor to neighbor interactions,
Yes.
magnetization being the same or opposite, and then you have the global field strength imposing a certain energy on everything
Exactly.
ubiquitously.
Yes. So this system is like one of the simplest system to study this phase transition. Like it shows this phase transition from one point to another point, from no magnetization to finite magnetization when you have H equals 0. But as we agreed before, if H is non-zero, there is no phase transition because there is no spontaneous symmetry breaking in the system. System already prefers a direction, so nothing weird happens there.
Now wait a minute. So like, I guess the neighbor to neighbor interactions, is it for all I and all j, or is it just for like I and j neighbors?
They consider it for all I and j. Like even if like you get a spin on one edge of the lattice and a spin on the other edge of the lattice, they can still see each other. It's a long range interaction.
Is that accounted for with like the distance? Like if they're farther apart, do they interact less?
No, like if they do, you're gonna have like something like an exponential e power minus the distance between I and j or something, like something that kills I and j, or 1
Yeah.
over I minus j, something that kills this. But here it's not. It's not considered like this.
Okay.
So yeah, it's like the original Ising model that was introduced was like the I and J were restricted to nearest neighbor interactions. But like for this system and for the Yang-Lee theorem, it does not. You do not have to restrict it to nearest neighbor interaction. The theorem still holds for without this. Okay. Okay, so what they did was actually quite smart. So what they did is they defined this little variable z. This is a small z that equals e to the power of 2 beta h, where h is your applied magnetic field. And they say that the partition function of that system, which is summing over all the microstates of e power minus beta times the energy of this microstate, has to be proportional to this quantity, uh, where Zn is like Z to the power of n is this, e power 2 beta Hn. And you see that this makes sense, like because like the An is coming from the interaction part, and the beta H is included in this Z. You could think about it like this. If I'm gonna sum over all the magnetizations, over all the spins that I have, that are all either up or down, I could move from like all the spins up. I will flip one down. This changes the interaction term, but I'm not gonna care about it. I'm just gonna put it here as some number. Or I could move 2 spins, or I could move 3 spins, or 4 spins, and so on. So this AN is just like the number of configurations with n excited spins above ground state, and including the factor, the interaction for those configurations. But the trick is you could write this function as a polynomial in z power n. That was their trick. Does this jump make sense now? Like writing it as a polynomial?
Is it like a perturbation expansion, basically? It's like you counting this excited spins.
Yes, but like I wouldn't call it perturbation. I would just call it just a rewriting of the summation. Like rather than considering the whole microstates as like microstate 1, microstate 2, microstate 3,
Yeah.
no, you just group all of them by these are all the states with all spins up. Then these are all the states with only one spin up. These are all the states with only 2 spins up, and so on.
Yeah. You
Yeah.
just rewrote it, but basically, I think coefficient's also kind of perturbative, right? The higher the n, maybe the smaller the coefficient, no? Oh,
Um,
maybe we'll show
if you're
it.
I think if you're perturbing it, like the low temperature expansion, for example, where you take just like perturbation above the ground states, you're gonna stop at a finite value that is less than the number of sites you have. But if you go up to all the number of sites, you considered all the possible values, so the expression is still exact.
Yeah,
That's
you
what I
wrote
mean.
it,
Yeah.
but basically you wrote it in such a way that you can do it up to less than n and still
Yeah,
get
yeah.
some precise, not
Answer.
exact, to some like lower precision, right? Result.
Yeah,
So that's
this is definitely correct. Yes.
yeah.
Yeah. So yeah. So now the trick is, as we said before, if I have Z, I know the free energy and I know everything about the system. Usually the problem in condensed matter is to find the partition function of the system. So if the partition function is given as a polynomial, people have studied polynomials for so long. So we know everything about polynomials. So what can we say about this thing? So first of all, we could see that if the free energy, if the partition function is a polynomial, then the free energy has to be analytic everywhere, except when the partition function vanishes from the complex analysis, because it just that's a true statement. Like f of z is proportional to log z. So if z is polynomial, it means that z is always finite, except at the infinities, and we don't care about the infinities. So if z is a finite value, then f is a finite value. So if z is analytic, f is analytic. And if f is analytic, no phase transition. Does this make sense?
Yeah.
Yeah. So the only interesting parts that could give phase transition is when z is 0, when z vanishes. Then f is going to be non-analytic. So it's going to admit some non-analyticity or discontinuity in the system. And so they said, okay, because this is a polynomial, we're just going to study the roots of this polynomial, z of z, the roots in this plane z, because it's easy to study the roots of the polynomial. Okay? So another thing is, because this is a polynomial, so the roots are mostly complex valued, because by the fundamental theorem of algebra, you have n roots, like the number of roots equal the number of sides, and you have only you have mostly complex roots. But for this f to be like to show phase transition for a given real physical value of z, this value has to be real and positive, because h has to be real. Okay, so this is the first thing we know.
Wait, so the
we're gonna
polynomial has real coefficients?
Yes, the polynomial has real coefficients, because all the coefficients are coming from just counting the number of states, and each state has e power minus sigma I sigma j to it.
So the
So
complex roots, I think that's what you just said. They'll be in conjugate pairs. The
yes, they
complex
will be
pairs.
in conjugate pairs. Yes, but like what I mean is, like, if you have a complex value z that gives you a root here, it means yes, f of z is going to be non-analytic at this complex value. But this doesn't mean a phase transition in the real system, because a complex value of z necessarily means not necessarily, but mostly means a complex value of h. So what does complex H mean? Complex magnetic field mean? It means nothing. So we should only care about when the roots are on the positive real axis. Because if I have a positive real value of z that gives me non-analytic f, then this means there is a real value of h that gives me non-analytic f. It's a very concise way of studying phase transition, and yeah, that's basically the Yang-Lee formalism. Does this make sense?
Yeah.
Yeah.
Isn't it like a complex magnetic field is just an electric field?
Complex magnetic field is just analytic field.
Electric field. Yeah.
Oh, that's actually interesting. I never thought about it this way. Um, because like the other part, the other part will be electric field. I don't know. I don't think they have considered this way. Like
Yeah, because it's uh, very common way of writing the electromagnetic field is just E plus I by B, right? So in a way,
yeah.
E is complex, it's just the same as E.
Yeah, no, this is a very good point. And maybe that would be like one way of studying an auxiliary system where electric field affects the system. But in our case, only magnetic field affects the system because we're studying ferro and para, like ferromagnetism, paramagnetism. So electric fields do not really affect what's going on because
Mhm.
spins do not feel them. Those are magnetic moments. But effectively, they should feel them in real materials. But in our simplified model, where this is just sigma up, sigma down, it doesn't feel any electric field. You know what I mean?
Yeah.
Yeah, it's a good point then. Yeah. Another thing to note is phase transition, as we said, appear only at in the thermodynamic limit. That's mean like your system has infinite number of particles. For finite number of particles, you don't see phase transitions, which means that uh, if I have a finite n, necessarily all the roots have to be complex. So none of them should lie on the positive real axis. They all have to be complex, and the real roots should only appear in the thermodynamic limit. The positive real roots should only appear in the thermodynamic limit. So yeah. So does this formalism make sense? Like basically the summary of what they did is, okay, let's consider this partition function as a polynomial in this variable z. And then to study phase transition, it is enough to see where the roots of this polynomial is. If the roots touch the positive real axis, then there is a phase transition. If they don't touch, then there is no phase transition. That's a very simple way of putting it. But correct, simple but correct way of putting it. Okay.
Yeah, sure.
Yeah. So we're gonna give an example on this, but we're first gonna talk about, okay, using this, what can they say? They say that if we take a ferromagnetic interaction, where like you take like different, not even the same interaction between all the spins, you take them differently. This could even be increasing with the INJ, but like it's just some, as long as it's positive, which means it's ferromagnetic, like the spins want to align together, all the roots of the polynomial z of z should lie on the unit circle in the complex z plane for any temperature. So the unit circle is the black line here. That's the z plane. Because it becomes confusing when I'm introducing this topic between jumping between z and h every time. So I made this plot and I hope it's clear. We agreed that z is e power 2 beta h. So if I want to get z from h, I go in this direction. If I want to get a beta h from z, I go to that direction. You know. So so basically, they say that all the roots have to lie on this unit circle here, the black one. The circles that are inside the unit disk, they map into the negative h here, and the circles outside the unit disk, they map into the positive h here. And due to the periodicity, like between this is argument 0, it goes all the way to 2 pi, or we could take it from minus pi to positive pi. The h-plane is just restricted to be from minus pi over 2 to positive pi over 2. So I have 3 random points, 1, 2, 3, and you can see how they map up to, like, different points in the h-plane. But the mapping is not so complicated. So their argument, or like their theorem, this is the infamous theorem. It says that if you have ferromagnetic interaction in any dimension, the interaction could be long range, like any range of interaction, and the geometry of the lattice in this dimension could be anything. It doesn't matter. As long as you have all the interaction ferromagnetic, the roots are gonna lie on the unit circle. So what does this mean physically? To understand things physically, we go to the h-plane. The unit circle is this line. This basically says all the roots have to have real part of h equals 0. Right? So of course, if you have a complex h, it's not physical. The only physical value across this is imaginary part of h equals 0. So they're basically saying if there is gonna be a root that gives a phase transition, it has to happen where imaginary h is 0 and real h is 0. It's like h equals 0.
Mm-hmm.
So this actually agrees with our observation before. We agree that if there is no magnetic field, if there is magnetic field, there should be no phase transition because the system always has magnetic field. It always has finite magnetization. It doesn't go to the paramagnetic state at all because the magnetic field forces the spin to be up. So what they did, okay, they said yes, they proved this mathematically in a very rigorous way, actually, showing that yes, your physical argument agrees with the math by showing the roots can only appear on on this imaginary axis, which means if they touch the real axis, it has to be at h equals 0. So only h equals 0 will give you phase transition. If you are here or at any other real h, you're not going to have phase transition because the partition function will not have any zeros.
Makes sense.
Yeah, it's a very strong statement because it's done for any dimension, any geometry, any range of interaction, but it agrees with the physical realization. And for example, like they did this in their paper actually in 1952. They found analytically the roots beta hn, like those roots of the partition function, and they showed that the roots look like this. So at very small beta, that's like high temperature. So the temperature increases like this. At very high temperature, there is a point where the roots do not pass beyond that, which means if you keep increasing the system size, the roots are gonna stuck here, keep filling this region more and more, but they are not gonna move forward. So it means for this temperature, you don't get phase transition. As you lower the temperature, this point extends even more, but it still stops. You lower the temperature even more, it keeps extending, but it stops. This indicates that there will be no phase transition, unless this point touches the real axis. And it does touch the real axis only when beta equals infinity. That's that's basically zero temperature. And this is a result known, like in one dimension, the system does not have finite magnetization unless you go to what's it called, unless you go to a zero temperature. So there is no phase transition in one dimension, as known.
In one
Does this
dimension.
make sense? In one dimension, yes, in one dimension. This is only for one dimension, for one-dimensional Ising model. Okay. So what about for two-dimensional Ising model? This one has a phase transition, the two-dimensional Ising model. So we could see that the roots, these roots are shown for like n equal 6 by 6 lattice. So you see that if you are above this critical temperature, like temperature is high but not critical for phase transition, all the roots stop at a point and there is some gap that's not going to touch the real axis. And then as you lower the temperature, the roots go closer to, like, the gap is smaller. But this gap is expected to close in the thermodynamic limit because you're close to the critical temperature. You are at critical temperature. So like the reason why it's not closing is because it's finite size. For this argument to make more sense, let's go to a temperature that is below the critical temperature, where we know there should be a phase transition. So you see that when we plot the roots just fill the entire imaginary axis, like all of it. So because it fills the entire imaginary axis, you expect that as n goes to infinity, those roots will just keep filling these gaps, and by filling the gaps, they will definitely hit the real value at the thermodynamic limit. So they say, okay, there is a phase transition in the thermodynamic limit, and it has to happen at h equals 0. So that's it.
Wait, but
Is this
here
one?
it's happening sooner than h equals 0.
Where? No, it's not happening.
At h equals 0, right?
Yeah.
Not
like
the
it's
beta.
not,
Beta is the temperature or the inverse of the temperature.
Yeah, beta is the inverse temperature. So beta small is high T, beta large is low T.
Right.
Yeah. And also like the effect that we talked about finite size, because it's like you say, okay, I'm below critical temperature. So they are not touching. They are close, but they are not touching. They will touch only in the thermodynamic limit when n goes to infinity. Yeah. So they basically told you don't have to worry about studying the system, because the thermodynamic way you have to look for the order parameter for every system. Look for the order parameter, and you look, okay, what quantity should I check for partial t by partial f, or partial f by partial t, or partial f by partial h? Which quantity is going to be discontinuous? It was like very cumbersome to study phase transition, but they just give you a very unified formalism. You just need to study the partition function and see where it vanishes in the complex plane, and that's it. So yeah, so this was the Yang-Lee zeros, but everything was done here was numerically rigorous, mathematically rigorous. So like everything was done through exact computation if it's numerical, and if it's analytical, it was done mathematically. So Stephen Wolfram studied the Ising model, the 2D Ising model, but from a computational point of view, from a little different in his book, New Kind of Science. So he said, okay, if I take the Ising model with no magnetic field, just ignore H. The energy of the Ising model is just given by this for a given configuration. And this Ij is on the nearest neighbor now, just nearest neighbor.
This is
And
one dimensional, right?
could you say it again?
This is one dimensional, not
Mm.
two.
Oh, no, I think this was two-dimensional.
No,
Was it one dimension?
pretty
No,
sure it's not.
well, like,
Just one.
okay, okay.
Well,
So
maybe not. Maybe I'll have to check it. Yeah.
yeah, it's like,
Anyway.
but you should expect this. It's like if it's in one dimension, you're not gonna see phase transition. It has to be in two dimension.
Okay, yeah, that
Yeah,
makes sense. Maybe
yeah.
yeah.
Yeah,
Okay.
maybe he had like an earlier draft with one dimension, and then what he actually put in the book was for the two-dimensional system, because he explicitly talks about phase transition shown here, and 1D does not have phase transition. Yeah. But like, so the way these graphs are generated is consider all the microstates, but rather than actually going to partition function and doing physics on it, just do some statistics on it. So for every given magnetization, let's plot the distribution of the energy for every given magnetization. Actually, for every given energy, let's plot the distribution of the magnetization. So what happens, like the way these graphs are generated is you fix a given energy and you see all the possible magnetizations for it. And the magnetization that happen with more states will be given a darker color. So for example, if we pick this energy, we see we have 1, 2, 3, 4 magnetizations. Those two happen with in many more microstates compared to the other two, to the lighter ones. Does this make sense? At very, very low temperatures, very, very low energy, those are the ground states, basically, you have two possible magnetizations, two microstates, all spins up or all spins down, which gives you the maximum possible magnetization, negative and positive, and only two of them, and equally likely because each happens only one time. Does this make sense?
This is like a two-dimensional histogram plot of
Yes.
microstates, and each microstate just goes into one of these, has two attributes, and you aggregate them for
Exactly.
this
Yeah.
plot. Okay.
Yeah.
You just simply enumerate all the spin chains, and you can
Mhm.
for every possible spin chain you compute the energy and magnetization, and just plot them.
Yeah,
Yeah.
I'll actually show the code I used to regenerate these graphs, but for the case of a magnetic field, not exactly these graphs. It's like the transpose of them, but yeah, I'm gonna show codes after this slide. That's my last slide. I just wanted to give an introduction because my project idea is really simple. It's small, so it wouldn't fit for an hour. And without the intro, just people feel lost. So I was like, I wanted to give a concise intro for Yang-Lee formalism. And as you can see that this is for if you take only n equal 3 by 3. This is a 3 by 3 system. If you take 4 by 4 or 5 by 5 system, you start seeing that, okay, it seems like for a given energy, there is always two possible magnetizations, and the thing is getting sharper and sharper. So the prediction that is in the infinite thermodynamic limit, for a given energy, you're gonna have a like for large energies, you're gonna have magnetizations like that is zero. It's not finite. But for very low energies, you have either a positive magnetization or a negative magnetization. So this is very similar to the graph of M and T that we shot, if you remember. And it's not really surprising because based on in the thermodynamics, a system that is at very high temperature, the system will probably have high energy. So at high temperature could be associated with high energies, and low temperature could be associated with low energies. So you could think about it like, okay, so a system with high temperature will have zero magnetization. A system with low temperature would have finite magnetization.
So for the n equals 3 and the n equals 5 case, this is a two-dimensional, like, they're looking at like a 3x3 grid. So you're
Yes.
looking at 9 total spin states. And
No, 2 power 9, because each one takes 2 spins up or down.
there are 9 atoms in the grid pattern, and then it's 2 to the 9
Yeah,
different ways for them to be
configuration.
assigned spins. But I
Yes.
guess the like on the n equals 4, you have like that rightmost point where you
Like
have
this one.
zero magnetization.
Mhm.
And I guess that's accomplished by having some sort of like anti-ferromagnetic configuration of like opposite. So you have like equal number of spin up and spin down, and that's a consequence of having an even number of total atoms in the arrangement. So for like
Yes.
the n equals 3 and n equals 5, you don't get that equilibrium, those equilibrium states.
Yes, exactly.
Okay.
So these are called a frustration due to edges. So generally, a square lattice is not frustrated. Like you could put it an infinite square lattice is not frustrated
Right.
because it could be broken into 2 sublattices. But if you have you odd number, it's like think about it like this. Like if you have an even number of sides, you could split them into half up and half down.
Yeah.
But if you have an odd number of sides, you can't actually split them in half up, half down. There has to be one more, which means you will get a zero magnetization for some values, but it's not the perfect anti-ferromagnetic one up, one down, one up, one down. So yeah. So yeah. So the question became, could we follow like basically this didn't talk about any partition function, this didn't talk about any thermodynamic potentials, it just considered distribution of magnetization for a given energy by considering all the states. Technically, this is a partition function because you have all the states, but without the computation. You just like look at this and look at this histogram, two-dimensional histogram, and you could find an indication of phase transitions, right? So what I was thinking, or what Stephen suggested, is could we, using this approach, could we say anything about the Li-Yang theorem, or like the Li-Yang approach about the zeros? And that was pretty confusing at first because the Li-Yang theorem is concerned with applying complex magnetic field. So how do you account for this in here? And that's basically that was my project idea that I'm gonna show from the notebook right now. Um, just I noticed that people are more comfortable with notebooks in Wolfram Institute, so I wanted to do this part here. So we again consider the Ising model. This we're gonna consider the simple case where I and j are nearest neighbor only, and uh, we're gonna introduce an imaginary magnetic field as Yang and Lee did. So the partition function of this h real plus I h imaginary is given by e power minus beta h, and we just write down everything that we have: an interaction term, a term for the real field, and a term for the imaginary field. That's just replacing this h here by h real plus I h imaginary and distributing it. This makes sense? Okay. So the Yang-Lee theorem, as we know it, is just saying that if z equals 0, if and only if the real part is 0. That's basically Yang-Lee theorem in a very confined language. So what I did was, rather than picking, these are the graphs that I just showed. So one could do something like this. One could take the energy to be only for the real part. That's like, just like the actual Hamiltonian when you have H. Call this the energy. That's your energy. And split the imaginary part on its own. Like just combined the real part that gives you energy of the system, physical energy of the system. And the imaginary part is just a phase, e power I beta H imaginary times the magnetization of the system. Okay. So this could be written as summing over all the possible energies and magnetization of this e power I beta H imaginary times m. And G of E and m is basically the number of states with energy the number of states with what's it called? With energy E and magnetization M that we defined like this. And if you think about it, it's just like this is the same as like this term is independent of E. So I could carry out the E summation over all the energies. And it's just the partition function becomes sum over magnetization, E power I beta H imaginary magnetization times the probability of this magnetization, of having this magnetization. So I just like when you sum all the energies with a given magnetization, I consider it the probability of having this magnetization or proportional to it. There's going to be a constant, but it doesn't matter for the zeros. Care about the zeros. Does this make sense?
Yeah.
Okay, so now if I just break down everything like this, it does seem like I'm just computing the average of a quantity that is a phase, right? So this, I just can write the partition function as it is proportional to the average of this quantity, the statistical average of a random variable m. Okay, so I could break this into a cosine part and a sine part. And I simply say, for z to be 0, I need both this average to be 0 and that average to be 0, because this is real and this is real, so they can't cancel one another. Like there is an I here. So what I'm gonna show here is that we can show that if H real is non-zero, I could show that sine is non-zero, which means the partition function is non-zero. I break one of those conditions.
Mhm.
Does this make sense? So
Yep.
we reached this partition function as a cosine term, like under the average, of course, and a sine term under the average. The only way that the partition function as a whole vanishes for a given h real and h imaginary is that this average vanishes and that average vanishes. I'm going to show that if h is non-zero, h real is non-zero, then the sine is non-zero computationally. Like I'm not going to show it analytically because what's the point of doing it analytically? So I'm going to show computationally that sine is likely not zero, which means that Yang-Lee theorem applies. You have, it's an approach to it, saying that it vanishes only if H real is zero. That's it. So is the logic clear?
Mhm.
Okay. So what I'm gonna do is, because now I'm concerned with the magnetization or the distribution of the magnetization, what I'm gonna do is, let's go up. These pictures are generated in a very similar manner to the other one, but rather than picking an energy and seeing what are the distribution of magnetization, I will pick a magnetization and we'll see what is the distribution of energies there. Okay?
Yeah.
Yeah. So what I could see is I could just like try to interpret this as the distribution of the magnetization in general as P of M. That's what I was trying to look for. So you could see that if you apply a negative field, the distribution is skewed towards a negative magnetization, which makes sense. So the average value of the magnetization is probably closer to a negative value. But when H is 0, you get a symmetry between positive and negative values of M. And when H is positive, you get the opposite, the other way around.
Huh. I'd be curious what happens
I'm not
if
sure
you
how's it different from the NKS pictures.
How is
I mean,
different from what?
from the Stevens pictures, just enumerating this histogram. Why it's not the same? Why there's no line?
Why there is no line? Because
Yeah.
think about it like this. So here you pick a specific energy, like this one, like this energy, and you see what are all the possible magnetization, right? So
I
you
don't think
see,
it's wrong like that. I think it's just literally enumerate all possible configurations, compute energy and magnetization, just plot it on 2D.
no, if you do this, you're not gonna get these curves here. What you're gonna get is just a very big blob in the middle. It's like saying most of your states have energy of almost zero and magnetization of almost zero, because most of them appear here.
No, I don't know. I doubt that for some reason. I have to try it
Well, like
again.
yeah, you could do it, but I don't know. I had it in one of my older notes when I was working on the project, but the only way that you could do this is like it's like you normalize every energy on its own. Like, for example, look at this. This is the ground state energy. It has only two magnetizations. These states happen with only one microstate. If you plot it with the same, like, strength as the states here that are of order 2 power 4, because, like, it's half of it, you're gonna get a number that is 1 compared to a number 2 power 4. That's gonna be definitely a white spot, and that's gonna be the dark spot. Because these happens 2 power 4 times, but this happens only one time. So in a plot
Yeah,
array,
it just normalized somehow.
yeah. So the way you normalize it, you have to like, even if you normalize with a scale, like, both of them go up or go down, difference is still the same. So you have to normalize every energy separately to generate this plot.
Okay.
Yeah. So like here, only for this ground state energy, this magnetization has half and this has half. That's the proper normalization. But here, you're just gonna compare things of the same order. You're gonna like here you divide by 2, but here you're gonna divide by 2 power 4 or
Okay.
2 power
So,
3.
so the difference between two pictures is whether you normalize columns or rows.
Exactly, yes. Here you normalize the columns, here I'm normalizing the rows.
Nice.
Okay.
Yeah.
Yeah. So, and the reason is like Stephen was trying to study magnetization as energy changes, but here I want to study the distribution of magnetization, not for a given energy, just as distribution of the magnetization as a whole, like the whole thing. So, and that's why, like, for H equals 0, you get a different picture. Like, now what's really dominating is for this magnetization, I have only this one energy, but for this magnetization, I don't care about all the other energies that were like creating an elongated line here. They just don't happen as much as these. So only this one appears.
So those are still there, but faint.
Yeah, these are
Or
still there, but faint, but really, really faint because
negligible.
they are, yeah, because now the line is normalized across the row rather than the column.
Okay.
And you can see now as we go closer and closer, we just expect a very, very thin line, or like a very, very thin distribution, as you would call it, like this. This is for n equal 14. That's 14 by 14 side. It's actually quite large. The biggest system is 16 by 16. The biggest exact solution for the Isaac model is 16 by 16. Yeah. And I actually have all of the, wait. I have all of my partition functions that I created like on the cloud. If anyone wants to take them and play with them, feel free to do so. And I could post the thing on the chat or in Discord for how to get the partition function. So, okay, what does this distribution tells me? It tells me that, I'm gonna zoom out a little bit just to show the sine function. Okay, so this is an average of a sine function. The sine function is an odd function in M, in the magnetization, right? So, if I'm leaning towards M negative, then definitely this sine function is unlikely to vanish because it will just keep taking contribution from the negative part, but not as much contribution from the positive part. And the opposite when H real is positive and equals 2. It will take contribution from this part, but not from that part. So when I compute the average, it's unlikely that the average is gonna vanish for that case or for that case. However, for this case, the sign is identically 0 because it's symmetric around M and M is odd. So you get same positive contribution and same negative contribution. So it vanishes for this. So this proves that it's unlikely that the partition function is gonna vanish if your H is not real. If your H is not 0. Your real H is not 0. So it's basically that statement. Your partition function will vanish only if H is 0. That's the same as it doesn't vanish if H is not 0. It's the same logical statement. So yeah, that was the idea of the project. And one could Just looking at this distribution, one could see why Li-Yang theorem is correct. It's because of this skewed distribution. If the distribution is not skewed, then this part is gonna vanish. So it does not tell you exactly where the partition function vanishes, because you still need to worry about the cosine part of the partition function, and cosine is even. So even if you consider this, you can't really tell much where the cosine is gonna vanish or not, or for what values. But at least you can talk about the imaginary part, saying the imaginary part is zero only if h is real is zero. This is enough to prove the statement that partition function cannot vanish if h real is not zero. One could further play with like, you know, the distribution. Not sure if I could. I hope it will run quickly. Yeah, so this is basically what I'm plotting here. Could move in a little bit. Yeah, what I'm plotting here is okay. So here, this is the distribution of m, and this is m. It's like probability of m as a function of m. M is normalized to be from -1 to 1, like divided by the number of sites we have. And this is the quantity that we were talking about, like for each of those. So you could see that. Let's pick a finite temperature like this. And this is H real. I think I should show it. So this is like some negative H real. And you see that the distribution is skewed towards the negative values. So, and let's pick some finite H imaginary. So you see that this P of M is just skewed towards this quantity. So if I want to plot sine beta HM multiplied by PM, which is like, you know, when adding all these, you get the average. When adding all these quantities, you get this average. When you add all of it, you see like no way that all those main negative contributions will cancel whatever comes from the positive distribution. It's very unlikely. Does this make sense? Yeah, it's just like another way of viewing it in a detailed manner. And it's the same, like, you know, as you change H imaginary. So yeah, if you apply a positive real field, you go to now the skewed is more towards the positive part. And you see, even if you get to very, very small, it's not taking the same contribution, even if they look similar.
Are these complementary? Is that 0.5 that where the line meets the real axis
This one?
corresponding to the peak of the other one?
Yes. Yes, it does. Yeah. Because actually, like the statement that I'm making for finite size are not exact, because, you know, like the statement of saying, you know, contribution is perfectly symmetric, that's not true unless you go to the thermodynamic limit, where you have, you know, perfectly for every magnetization, there is one energy that's gonna dominate, like until that thing is perfectly fine, you know, like perfectly thin. And in that limit, your magnetization is gonna be like, okay, this will keeps getting narrower and narrower, like the width of this, and then picking only one point. So the only way that you're gonna get it is you have, like, you know, 1 point here and 1 point here, like setting h equals 0, like this. I could just set it to be 0, I guess. Yeah, my hand. Yeah, and then you can see now this is perfectly symmetric around it. So yeah.
For those plots up above, like I wonder what happens when h is like negative 0.5 or something, like when it's closer to 0 but not actually equal to 0. So you get sort of.
I did for one. I did for one, for -1 and +1. The reason why I'm doing this in like discrete steps of 2 like this, is the way I generated this partition function. It was for another project where the partition function is expressed as a polynomial in the variable z and u. Z is what we defined, and u is something really similar, but for beta times the interaction term rather than the magnetic field term. So it's a polynomial thing. So I wasn't able to like on a week. I just worked on it in half of the project. The other half I was working on a different idea. The earlier half is called the Asana contraction. So when I switched it, I didn't have time to regenerate the partition functions for the new Hamiltonians, like in a proper format. But so I had to work out with what I had earlier. So the way I generate this is I get the coefficient list of a multivariate polynomial, of a two-variable polynomial. So the coefficient list is kind of forcing me to apply only integer magnetic fields, and this integer has to be similar to the values of the powers you have in the polynomial to take it out. But with some extra, like I think coding, you could get the exact Hamiltonian, the exact partition function, and you could just apply the magnetic field just by counting it. It's really hard doing 2 power 8. Actually, the limit would be the limit for the exact enumeration is gonna be like 4 by 4 or 5 by 5 if you have like a very very powerful computer. To get 8 and 14, I had to use other ways of diagonalizing the Hamiltonian or like a final partition function. So that's why I had to commit between these two. But what's gonna happen is something like this. This edge is gonna just keep like this peak is gonna move closer to the 0, and this edge is gonna extend
Okay. Yeah.
until you get that value. We get to h equals 0. And then when you move, this peak, like this edge will keep moving, and the peak will start moving down. Does this make more sense?
Mhm.
It's just like, the motion. It's like there should be some continuous motion of the distribution from here to here for all of them.
Cool. We have a question from Thomas Murph. Is there any merit in the hypergraph theoretic aspects of these icing models, I guess?
If there is any, so the thing that we were working on is, think about it like this. For the Ising model, you're basically dealing with configurations. What you could do is you could attach each configuration, like you could create a causal graph between each configuration as you span all the possible configurations, where like in a causal graph, each two nodes are connected with a cause, and the cause here is a spin flip. So you start from all the spins up, and then you flip one spin and you get a new node.
Yeah.
Yeah, and then like you flip another spin. This spin could be close to it or far from it, which gives you two more nodes, and so on until you reach the other case where you have all the spins up. That would be like a full causal graph on it. However, it's like in the graph language, what we tried in the first project was like to use the graph language for this Asana contraction thing. The problem with it is it doesn't give you much advancement computationally because you're considering all the possible states. So what's the point of putting it in a causal graph? What I could see as a good advancement is there was a Wolfram project. I think a paper is coming out soon on the hard sphere model, where I think Xerxes was modeling hard spheres colliding with one another, just like a Monte Carlo simulation of hard spheres colliding with one another, and creating a causal graph from this. But the causal graph, rather than considering every microstate, it considers only the collisions. So I was thinking a similar thing that could be done in terms of causal graphs is rather than considering all the possible microstates, consider only those states that that are in a Monte Carlo simulation that actually lower the energy, or do you have specific kinds of flip spins? So this way you reduce the number of the configuration space that you have. I think with 2 power ns, you're probably going to deal with much lower number. And now you could do analysis, like a graph analysis on the causal graph you get, and you see what kind of physics you're going to study from there, rather than finding all the possible states.
Yeah, that's interesting.
Yeah, it's going to be a different way of viewing Ising model, and it's a new one, but I didn't have time to study that far.
You can probably do this perturbative thing again, right? In the beginning, we mentioned that polynomial doesn't have to be summed to the end, right?
Well, like
So
Actually, like for the specific case of the Ising model, the polynomials need to only be summed to the midpoint because the polynomial is symmetric. Like, the coefficient of 1 of z power 0 is like no spins up is the same as the coefficient of z power n, all spins up. It's the same coefficient. And you could see the symmetry. It's like symmetry coming from if you flip all the spins, you still have the same energy. You just flip the sign of the magnetization. So that's the symmetry there. But what you could do is like, rather than going all the way up to ns over 2, you could go up to ns over 4, maybe. But you have to be careful of what region or what you're interested in. If you take only like for the ferromagnetic case, you could do the cutoff that you're thinking of because most cases are gonna be included in the edges, like that's where the interesting physics happens, where you go all the states are actually aligned with in a specific direction. But for the antiferromagnetic case, you can't do this because the state with like half the magnetization or zero magnetization, this is the interesting one. You can't just ignore it. So you have to include this, and you can ignore the edges. So you need to be careful what part of the polynomial you cut off.
Yeah. I'm also thinking about whether there's a without doing this hard cutoff, but do something similar to Feynman diagrams, right? So that you can basically have some better structure of enumerating those things in your sum, right? So that it's like maybe enumerating some topology of causal graphs, or which
Yeah,
you interpret as Feynman diagrams, and you enumerate those instead.
yeah. I think actually, Manu. Yeah, I definitely want to. Like I didn't formally conclude my talk, but I'm done. And of course, the one who suggested this direction was Stephen Wolfram, and I'm really thankful for Manu for like her help in this. And she was my mentor in the project. And like this idea of expressing it like this is coming from many discussions with my advisor, Professor Shram Shastri. So I just want to mention those three people. And then on your question, Nick, about Feynman diagrams, I think Manu is actually working on something like this, but with the Hubbard model. Uh, but yeah, I think she is trying to like lower down the dimension of the configuration space by considering, not lower it down, but like lower down the complexity of enumeration by considering Feynman diagrams of those spin flips. But in her case, it's like Hubbard model, so it's spin hopping, not spin flips. Like it goes from one side to another side. But it's this should be mapping. But
Yeah.
yeah, it's definitely
There's
interesting
also
case.
there's also like a known mapping between correspondence between Ising chain and Dirac propagator. So in a way, you can the weak rotation that you do, this famous correspondence of your inverse temperature and imaginary time, right? That basically your correspondence between statistical mechanics and quantum mechanics. You can basically treat your Ising chain, the statistical mechanics, statistical analysis of what we've done here, as a quantum mechanical system, and there it just behaves like a particle propagating in time. So in a way, you're enumerating not the spin chain configurations, but all possible paths, like of a particle zigzagging on a space-time diagram lattice, like on a space-time lattice, right? And for that
Yeah.
one, basically, it's more straightforwardly you can find the correspondence to Feynman diagrams because it's basically doing quantum field theory on a lattice, and you just
Yeah.
propagator, which is your particle, and you can also assume that you have interaction. Well, basically your mass is given by exactly the probability of zigzagging or this spin flipping in your case, right? So it's like a mass is more equivalent to the temperature. The higher the mass, the more bouncing it does. So the more probability it is to change the spin. But this correspondence, basically, you can think of this problem from this completely two different directions.
Yeah, that would be really interesting. And you know, there is actually a mapping for the Ising model of zero magnetic field. Like the problem is exactly solvable when you don't have magnetic field, but when you do have magnetic field, it's not exactly solvable. So I wonder if anyone has tried these directions for the one with the magnetic field to show the to find the exact solution. But yeah, it's definitely. an interesting approach.
Yeah.
Actually,
No,
like,
I found some literature on this extension of this zigzagging model, which is basically called Feynman checkerboard, right?
mhm.
It was proposed by Feynman himself of that limits to the Dirac propagate and Dirac equation, and in the way you can also introduce the gauge field into it by you can also do it.
Oh,
I,
okay.
I, I
So,
don't, I don't I don't think there's an analytical solution to that, but technically you can also study these models, and it's also related to quantum box and quantum cellular automatons. You basically formulate the same model as a quantum version of cellular automata. You just have uh, some propagator that zigzagging the particle, just moving it left to right, or the actual gauge field, just counting those. And
mhm.
that's basically now you have a interaction with the field. So that's the same as having an interaction with your magnetic one.
Yeah,
So
that's really interesting. Oh yeah, I will definitely consider it. Like most of my work is on classical Ising model. So I did take like quantum many-body physics class, and I heard of like the Feynman path integral, and I worked it in homeworks, but that was like long time ago. But I'm not like I don't have like immediate response if there is a limitation to this approach. But the way you described it, I don't think there is, uh, at least not on the top of my head.
mm, cool.
Well, like something interesting is like when you mentioned the imaginary part and like the correspondence between the time, the imaginary time as a thermodynamic property and the actual time propagation in quantum mechanics. It reminded me of something that people did, which is actually it's better if I explain it on this picture. It's like people try to view this as what's it called? It's quite a similar idea to this one, but like they considered here beta times h imaginary as some like they created a model like a spin system. An experiment that actually the coherent time between the coherence time between the spins is given by something that looks like this, where beta h imaginary corresponds to the actual time, the actual propagation time in real life. And they just showed that every time uh, the actual time hits one of those values where z is zero, it just like the coherence became zero. Like there was no coherence between the spins, and then it goes up again, and then it hits at the next zero. So they could show a one-to-one correspondence between those points, h imaginary, where there are zeros of the partition function, and the coherence between spins in the system, like not spin, like qubits between quantum qubits in a quantum computing circuit.
Okay.
It was really interesting, and it was recent. I think that was like in I think 2018 or something. So yeah, the zeros have been studied experimentally and have been mapped to other systems. So it's still a rich problem.
Makes sense when you have like this complex amplitude. You're basically starting doing quantum mechanics at this point.
Exactly, yeah. And I feel like, like this is the poor man version of it by just considering this phase as like, a quantity that you're measuring, or like taking the average of thermal average of. It's just like a poor man version of that statement, of that connection. Uh, it makes definitely more sense than thinking, hey, what is a complex magnetic field in real life? You just don't think of it that way. That's
Yeah.
basically
So like I said,
it.
it's probably electric field. So
Yeah, I guess if
yeah.
like I don't know if anyone like who works on magnetism that actually considers an electric field on the system and puts it as an imaginary magnetic field. Like the wave itself, yes, it's expressed like this, but it's expressed like this only to explain the phase difference between the the electric component of the field and the magnetic component of the field, right? Because they are out of phase. Like when this is maximum, this is minimum. But like, I don't know if like, people actually express the magnetic field as this because they will do all the algebra with the complex notation, but at the end they will take the real part or the imaginary part
A
for
bit
the,
weird. I don't know.
yeah.
For me, it seems natural, or at least worth exploring. It's like,
Yeah.
what is a magnetic field? It's just an electric field if you boost your reference frame. It's like they're not different.
No, yeah, they are not different. But like boosting your reference frame is a dynamical property, and the partition function here is called the equilibrium partition function. So it cannot include any kind of dynamics. Like, you do the thing and you wait. So I don't know if there is a partition like in relativistic statistical mechanics. There is relativistic statistical mechanics, but I don't know if the partition function there is defined in the same sense. It's like yeah, I'm not sure honestly.
Yeah, it seems weird that it's like if someone deals with a magnetic field, an electromagnetic field, special relativity has to be taken into account somehow. At
Definitely.
least implicitly.
Yeah, well, like generally, like complex variables in physics I usually like to think of them like this. You have two things that do not talk to one another. They are linearly independent. They can't mix with one another, like the electric field and magnetic field. You're not gonna find the electric field killing the magnetic field in your reference, in the same reference frame, of course. So it's like expressing them as E plus IB seems natural, because they're not gonna talk to one another. They're gonna affect each other. And like it's like even away from general like relativistic electrodynamics, if you go to waveguides, people express the attenuation in from an electric field, like electromagnetic wave into material. The attenuation is given as like the imaginary part of the refractive index, like the refractive index be extended to be complex. So it's like the real part is gonna still describe the refraction, but the imaginary part is gonna describe the attenuation or like the killing of it. So it's like whenever you have two quantities that do not affect one another, just physicists like to write them in one line, like rather than in two lines in a complex value.
Mhm.
I had a question about the visualization. I was wondering, did you try doing those plots as like distribution charts? Is that possible?
What do you mean by distribution charts? Oh, I'm not familiar with
Like,
distribution charts.
3D?
I mean, it's just a function it's a built-in function, but instead of showing the like the faded, yeah, I mean, I'm not entirely sure what exactly this is even showing, but I'm pretty sure that it could look nice if you do it like that.
I think it should be.
I see. I see what you mean. Oh yeah, actually, yeah. I think this would look interesting. Yeah, yeah. This is okay. I think I know what the problem could be. Is that
Mm-hmm.
it's the discreteness. Like here
Right,
it seems like you can check the distribution of a given quantity. Like you have some sort of a categorical variable that you change, like for A,
right,
B,
right,
C,
right.
and so on. And you have a continuous variable that you want to measure its distribution for a categorical value, like from data analysis. The problem here would be coming from like if I want to check the distribution for this, is like the values m are really really close to one another, so I'm just not gonna get much when I plot it
I
plot
see.
it against A. Like you see, like it's gonna be like it's like visually it's not gonna tell you much. That
Right,
would be the problem with that. But here it's
right,
just like the color just indicates the amount that you have, and that's it, without looking at distribution.
right.
Yeah.
You can
Yeah,
do it in 3D at least.
Yeah,
With
in
the actual
3D that
plot.
would be interesting. Yeah,
It's just a discrete plot 3D.
yeah.
So this,
That's how I started this project. It's like I wanted to do this plot in 3 dimension where like I talk about real magnetization and some kind of complex magnetization, but I just didn't get it to work. Like showing that they have to cancel each other somehow for the real or for the imaginary. But
I mean, like even this plot is just you instead of the color, the density of color, you just have a column height.
oh
That's
yeah,
it.
in the 3 dimension,
Yeah.
yeah. Yeah, yeah. So in this case, distribution chart would look nice because now you have discrete values in the M, so you could
Yeah,
just
yeah. It's like a
yeah,
discrete plot 3D you can use. You can
yeah.
instead of distribution, it's a discrete plot 3D function.
Okay. Uh, oh, this one. Okay.
The 3D version. 3D.
Yeah. Okay. Yeah. That's definitely also interesting. Actually, this might help in like, viewing. Okay, now assume we stick to this real H. And we know the sine part is 0. What about the cosine part? Can we even study where the cosine part becomes 0? I think this picture, like this view, like the computational view that Stephen suggested, should be able to tell you this, but not from here, because here, cosine from this is the same as from this. You just get double the contribution up to here. But where exactly does it cancel here, like in this region? Maybe the three-dimensional part will make more sense.
All right, cool. Gonna shut down the stream now. Thank you so much, Ahmed, for coming on and presenting.
Sure. Thank you for inviting me.
Thanks everyone for tuning in and for your questions. See you again next time.
Okay.
All right.